Christmas Eve 1997. Families across New Zealand were settling into their celebrations, wrapping final gifts, preparing for midnight church services. On the overnight express from Wellington to Auckland, 151 passengers dozed or read, anticipating reunions with loved ones waiting at the journey's end. None of them were thinking about the mountain in the distance, the one with the lake at its summit that had turned an electric blue weeks earlier, a color that meant something, if only anyone had known precisely what. 40 kilometers away, in the darkness at the top of Mount Ruapehu, a dam of ice and volcanic debris was failing. 1.4 million cubic meters of scalding acidic water began to move, accelerating down the mountain at speeds approaching 100 kilometers per hour, transforming into a wall of mud and boulders and obliterated forest that scoured everything from the valley floor. The sound was apocalyptic, but there was no one in those remote upper slopes to hear it. No one to send a warning to the railway bridge at Tangiwai that lay directly in the path of what was coming. At 11:49 p.m., the Tangiwai bridge collapsed into the lahar just as the locomotive reached it. 6 carriages plunged into the torrent. By the time the sun rose on Christmas morning, 121 people were dead, and New Zealand had learned a terrible lesson about a lake that changes color. But here is what makes this story even more unsettling. The scientists knew the crater rim would fail. They knew the lake was refilling. They knew that when it breached, a lahar would follow. What they couldn't know, what they still struggle to predict with certainty today, is exactly when. And in that gap between knowledge and prediction, between understanding a system and controlling it, lies one of volcanology's most haunting challenges. Mount Ruapehu's crater lake doesn't just change color for aesthetic reasons. Each hue is a message, a chemical sentence describing what is happening in the magma chamber kilometers below. Gray means quiet. Green means awakening. Turquoise means the volcano is breathing hard, pumping sulfur dioxide into the water, heating it toward boiling. Electric blue means you should be paying very close attention, because something is building beneath the surface. Something that might erupt tomorrow or might wait another year, and the lake itself cannot tell you which. This is the story of that lake, of the volcano beneath it, and of the scientists who have spent decades trying to learn its language fluently enough to know when a color change is merely interesting and when it is a countdown to catastrophe. It is a story about living on a restless planet, about the beauty and terror of geological forces that operate on their own timeline, indifferent to human schedules and Christmas celebrations and trains running on time. How does a lake change color? Why does it matter? And what does it mean when the water at Ruapehu's summit turns that particular shade of blue that scientists have learned to recognize as the color of a volcano gathering its strength? Let us take you back to where this story truly begins, not on that tragic Christmas Eve, but decades earlier, to a mountain that the Mbori knew was sacred for very specific reasons, and to a time when the first European settlers looked up at the snow-capped peak and had absolutely no idea what they were building their ski resorts upon. In the heart of New Zealand's North Island, where tectonic plates embrace and wound each other in the same ancient gesture, rises a mountain that defies the very idea of permanence. Mount Ruapehu stands at 2,797 meters above sea level, a giant cloaked in snow and silence, dominating the horizon of Tongariro National Park like a sentinel that has watched over this land since time immemorial. The Maori people who first walked these volcanic slopes knew this mountain by many names, but perhaps the most poetic was Te Wai Jimo, the water of dreams. For them, Ruapehu was never merely stone and ice. It was tapu, sacred beyond measure, a place where the spirits of ancestors dwelled and where the living were required to tread with profound respect. The mountain was woven into their cosmology, their songs, their warnings passed down through generations. They understood what the Europeans who arrived centuries later would take far too long to learn, that Ruapehu was alive in ways that transcended the biological definition of life. But there is something peculiar about this mountain, something that no atlas can fully capture, no photograph can entirely convey. Ruapehu refuses to remain the same from one year to the next. Sometimes it changes from one month to the next, and on rare occasions from one day to another. This is not the gradual erosion that shapes all mountains over geological epochs. This is something far more immediate, far more unsettling. Hidden at the summit, like a secret the mountain keeps close to its heart, lies a crater lake. But calling it simply a lake feels inadequate, almost dishonest. This body of water behaves like no other on Earth. It changes color as if possessed by some chromatic spirit. Ash gray 1 week, emerald green the next, brilliant turquoise after that, and occasionally a sulfurous yellow that speaks of chemical violence occurring in the depths below. The lake's temperature is equally capricious, ranging from pleasantly cool to literally boiling, with surface temperatures that have been recorded at over 80 degrees Celsius. For decades throughout the 20th century, thousands of tourists descended Ruapehu's snow-covered slopes, their skis cutting elegant arcs through pristine powder, blissfully unaware that beneath them, sometimes only a few hundred meters down, a vast hydrothermal system breathed and pulsed with geothermal energy. The mountain had become one of New Zealand's premier ski destinations, with chairlifts and lodges and all the infrastructure of modern recreation built upon the flanks of an active volcano. Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. Imagine, it's the 19th century. European settlers arrive in New Zealand, gazing upon a mountain that seems like a piece of the Alps transplanted to the Pacific. Snow-capped peaks, pristine slopes, an absolute paradise. They called it Ruapehu, but this mountain held a secret, a paradox. It was both an idyllic wonderland and a simmering cauldron of immense power. This is the story of humanity's relationship with a sleeping giant, a story of attempts to tame the untamable. In the early days, people tried to domesticate the giant. Vintage photographs show charming wooden chalets and rustic observation posts built right on its flanks. Skiers dotted the slopes, carving lines into the snow. It was a picture of serene control, an attempt to discipline the wilderness and bend it to human will. Ruapehu became a playground, a place for recreation and adventure. But the mountain was only playing along, its true nature hidden just beneath the surface, waiting for the right moment to reveal itself. The people who built their dreams on these slopes were living on the edge of a power they couldn't yet comprehend. The heart of the mountain and the key to its mood is the crater lake. From a distance, it can look like a tranquil, high-altitude pool of water. But up close, it's a different story. Its color is never constant. One day, it might be a calm, placid blue-gray. The next, it could shift to a vibrant, almost electric turquoise or a murky, ominous green. These color changes aren't just for show. They're a visual warning system. They are the direct result of gases and heat rising from the magma chamber deep below. The lake is a living, breathing indicator of the colossal forces at work, a mood ring for one of the most active volcanoes in the world. To look into its depths is to look into the very throat of the Earth. After the turmoil of the Second World War, a sense of peace returned to New Zealand. People were eager to reclaim a sense of normalcy and joy. On the slopes of Ruapehu, skiers returned, their laughter echoing across the snow. The mountain seemed to share in this post-war tranquility. It was a perfect day, March 24, 1945. Skiers were enjoying the pristine conditions, completely unaware of the pressure building beneath them. Then, with shocking suddenness, the mountain roared to life. A violent eruption tore through the crater, blasting a column of steam, ash, and rock thousands of feet into the sky. The paradise was shattered. The skiers fled in terror as the sky turned dark. The 1945 eruption was a brutal reminder that Ruapehu was not a passive landscape. It was a dynamic and incredibly dangerous force of nature. The 1945 eruption was a wake-up call for the scientific community. It was no longer enough to simply admire the mountain. It needed to be understood. A new era of observation began. Scientists set up instruments, took regular samples from the crater lake, and flew over the summit to monitor its every change. They watched as ash clouds billowed from the vent, and they meticulously tracked the thermal fluctuations in the lake's water. They were learning to read Ruapehu's language to interpret the subtle signs that preceded an eruption. The crater lake, with its shifting colors and temperatures, became their primary focus. They were beginning to understand it not just as a body of water, but as a real-time gauge of volcanic activity, a natural early warning system that could potentially save lives. The lessons learned in 1945 were put to the test just over 2 decades later. Starting in 1969, Ruapehu entered a more sustained and dramatic cycle of activity. This wasn't just a single, explosive event. For months, the crater lake was in a state of turmoil. It boiled and seethed, throwing spectacular jets of steam and superheated water high into the air. The real terror, however, came in the form of lahars. These are volcanic mudflows, a terrifying slurry of water, rock, and ash. When the Crater Lake's dam would breach, these lahars would come screaming down the mountain's flanks at incredible speeds, carving new paths through the landscape and destroying everything in their way. Footage from this time is chilling. It shows the raw, destructive power of the volcano, a force that could sweep away bridges and roads in an instant. The 1969 cycle demonstrated that Ruapehu's danger wasn't just in what it threw up, but also in what it sent rushing down. From then on, the mountain continued its cycle of calm and chaos. In 1995 and 1996, Ruapehu put on one of its most spectacular displays in recent memory. The eruptions were massive, sending towering ash plumes more than 10 kilometers into the atmosphere, visible from hundreds of kilometers away. The crater lake was completely emptied, blasted away into steam and ash, leaving a raw, steaming 700-meter-wide crater. For months, the mountain dominated the news. Air traffic was disrupted across the country. Ski fields were closed, buried under a thick layer of gritty gray ash. Scientists worked around the clock, using a new generation of sophisticated monitoring equipment to track the volcano's every tremor and burp. This event was a modern spectacle, a powerful volcanic display broadcast to the world, showcasing the latest in scientific monitoring and our evolving ability to live alongside such a formidable natural power. But even with all our science and technology, Ruapehu always has the final say. In 2007, a surprise eruption occurred. Without the classic warning signs that scientists had come to expect, a hydrothermal explosion shot a column of ash and rock into the air. A lahar was triggered, which, thankfully, was diverted by a newly engineered barrier, preventing a disaster on the scale of the past. This event was a humbling lesson. It proved that even when we think we understand the mountain, it can still surprise us. Our monitoring systems are incredible tools, but they don't give us control. They only give us a chance to get out of the way. Ruapehu operates on geological time on a scale far beyond human lifetimes, and it will always have secrets that we have yet to uncover. So, what is the legacy of Ruapehu? It is a story of a profound paradox. It's a place of breathtaking beauty and immense danger, a skier's paradise built on the lid of a magma chamber. It is a constant living reminder of the raw power that shapes our planet. We build our chalets, our ski lifts, and our monitoring stations on its slopes, but we are only ever temporary guests. Ruapehu teaches us humility. It shows us that for all our ingenuity and technology, we do not command nature. We are part of it, subject to its winds and its power. The mountain stands as a silent, majestic sentinel, an untamable force that reminds us we live on a dynamic, ancient, and powerful world. Thank you so much for joining me on this journey to the heart of Mount Ruapehu. If you found this story as fascinating as I do, please hit that like button and subscribe for more explorations into our incredible world. See you next time. Have you ever seen a lake that changes color like a mood ring? High up on Mount Ruapehu in New Zealand, there's a crater lake that does just that. It's not magic, it's chemistry, and it's one of the most fascinating natural laboratories on Earth. Today, we're diving deep into the science behind this incredible phenomenon. What makes this lake switch from a serene turquoise blue to a stormy battleship gray? And what can these color changes tell us about the massive, restless volcano slumbering beneath? Mount Ruapehu isn't just a mountain. It's an active stratovolcano, and its crater lake, known as Tangiwai, is essentially the top of its plumbing system. This isn't your average swimming hole. It's a hot, acidic, and dynamic body of water that acts as a window into the volcano's soul. Scientists watch it constantly because its changes can signal what's happening deep within the magma chamber. The lake's temperature can swing from a chilly 10 degrees Celsius to a scalding 60 degrees. And its acidity can be as strong as battery acid, with a pH as low as 0.5. Imagine a lake full of sulfuric and hydrochloric acid. That's what we're dealing with. So let's talk about the colors. When the lake turns a milky, uniform gray, it's often a sign of increased activity. This gray color comes from fine rock particles or rock flour stirred up from the lake bed by gas and fluids rising from the vents below. Think of it like stirring up sediment at the bottom of a glass of water. When volcanic gases like sulfur dioxide and carbon dioxide bubble up more vigorously, they agitate the lake floor, kicking up these tiny particles and turning the water opaque and gray. This often coincides with a rise in temperature, indicating that more heat and gas are being released from the magma system. It's the volcano's way of clearing its throat. But what about when it's a beautiful, vibrant green or blue? These colors tell a different story. When the volcano is in a quieter state, the sediment settles down. The water becomes clearer, and now chemistry takes over the color palette. The striking emerald green and turquoise blue hues are caused by dissolved minerals, particularly sulfur and iron, interacting with sunlight. When sulfur is in a dissolved elemental form, it creates tiny particles that scatter sunlight in a specific way, producing a brilliant green color. The exact shade of green can depend on the concentration and size of these sulfur particles. The transition to a clear, deep blue is even more interesting. This happens when the lake is very calm and has had time to clean itself. The fine sulfur and mineral particles either dissolve completely or settle to the bottom, leaving the water incredibly transparent. When sunlight hits this pure, clear water, it behaves just like it does in the deep ocean. The water absorbs the longer wavelengths of light, the reds, oranges, and yellows, and scatters the shorter, blue wavelengths back to our eyes. So a blue lake is a sign of a very stable and quiet period for the volcano. It's Ruapehu in its most peaceful state. You might be wondering, how do scientists keep an eye on a lake that's sitting on top of an active volcano? They don't just rely on pretty pictures. They use a whole arsenal of high-tech tools. Satellites monitor the lake's temperature and chemical composition from space. On the ground, a network of seismometers listens for the faintest tremors, which are tiny earthquakes caused by magma and gas moving underground. GPS stations measure even the slightest swelling or deflation of the volcano's flanks, which can indicate that magma is accumulating below. And of course, there are the brave scientists from GNS Science, New Zealand's Geological Survey, who make regular trips to the crater rim to collect water samples. It's a risky job. They have to be mindful of the weather, the volcanic risk, and the toxic gases. These water samples are then taken back to the lab and analyzed for changes in their chemical makeup. Are certain elements like magnesium or chloride increasing? This could mean fresh magma is interacting with the hydrothermal system. The combination of all this data, the lake's color, temperature, acidity, gas emissions, and seismic activity, helps create a comprehensive picture of what Ruapehu is up to. To really understand why this lake is so active, we need to zoom out and look at the bigger picture, the tectonics. New Zealand sits on the Pacific Ring of Fire, right where the Pacific Plate is diving or subducting beneath the Australian Plate. This process is messy. As the Pacific Plate sinks into the Earth's mantle, it heats up, and water trapped in the crust is released. This water lowers the melting point of the surrounding rock, creating magma. This magma is less dense than the rock around it, so it begins to rise, eventually forming the chain of volcanoes that make up the Taupo volcanic zone, with Ruapehu being the magnificent southern anchor. The magma beneath Ruapehu isn't just one big pool. It's a complex network of chambers and conduits, a bit like the root system of a giant tree extending miles into the Earth's crust. It's the interaction of this deep magma with the shallower groundwater and hydrothermal systems that fuels the drama in the crater lake. The lake is the very top of this intricate plumbing, making it a uniquely sensitive and visible gauge of the volcano's health. So the next time you see a photo of Mount Ruapehu's crater lake, you'll know that its color is more than just a pretty shade. A stormy gray tells a story of unrest, of gas and heat rising from the depths. A brilliant green speaks of dissolved elements painting the water with chemistry. And a serene blue signals a time of calm and stability. Each color is a chapter in the ongoing saga of a living, breathing volcano. It's a powerful reminder of the incredible forces at work beneath our feet, constantly shaping our world in the most beautiful and dramatic ways. This magnificent lake isn't just a geological feature. It's a dynamic and colorful conversation between the deep earth and the sky. Thanks for joining us on this journey to the top of Mount Ruapehu. If you found this as fascinating as I do, make sure to hit that like button and subscribe for more deep dives into the wonders of our planet. Let us know in the comments what other natural phenomena you'd like us to explore. See you in the next video. Deep beneath the calm waters of the South Pacific, a colossal geological drama is unfolding. The Pacific Plate, a massive slab of Earth's crust, is slowly but relentlessly diving beneath the Australian Plate. This process, known as subduction, is the very first act in the life story of one of New Zealand's most active and awe-inspiring volcanoes, Mount Ruapehu. As the Pacific plate descends, it drags water-rich ocean sediments with it deep into the Earth's mantle. Under immense heat and pressure, this water is squeezed out, lowering the melting point of the surrounding rock. This creates magma, a molten brew of rock and dissolved gases, which is less dense than the solid rock around it. Like a hot air balloon, this magma begins its slow, determined ascent towards the surface. A journey that can take thousands of years. This isn't just one big blob of magma, though. Imagine a complex plumbing system deep underground. The magma collects in a series of interconnected chambers and sills, forming a mush-like reservoir. It's a dynamic, ever-changing environment where different batches of magma mix and mingle. Some of it cools and crystallizes while fresh, hotter magma is injected from below, re-energizing the system. This intricate network of stored magma is the engine that powers Ruapehu's fiery heart. Now, let's bring this story to the surface. Perched atop this restless giant is a unique feature. A crater lake Tangiwai. This isn't just a picturesque mountain lake. It's a key player in Ruapehu's eruptive style. When hot magma rises close to the surface, it heats the rock beneath the lake, which in turn heats the lake water itself. This creates a hydrothermal system, a high-pressure cooker of superheated water and steam sealed by the weight of the lake above. When an eruption finally happens, it's often because a fresh pulse of magma or gas breaks through this seal. The result is what geologists call a phreatic or phreatomagmatic eruption. Think of it like dropping water onto a sizzling hot pan, but on a terrifyingly massive scale. The near-instantaneous conversion of water to steam is incredibly explosive. It unleashes a tremendous amount of energy, blasting rock, ash, and superheated water high into the sky. The physics of this process is fascinating. The rapid depressurization causes dissolved gases within the magma, like water vapor and carbon dioxide, to violently expand and escape. This fragmentation shatters the magma into tiny particles we call volcanic ash. This mixture of steam, gas, and rock fragments erupts as a turbulent, high-speed column. It's a chaotic and powerful display of nature's force, driven by the violent interaction between fire and ice. But the danger doesn't end when the eruption column falls back to Earth. In fact, for Ruapehu, that's often just the beginning. The ejected water from the crater lake, along with rapidly melting snow and ice from the volcano's glaciers, mixes with loose volcanic debris on the slopes. This creates a lahar. A lahar is not just a flood or a landslide. It's a terrifying slurry of water, rock, and mud that flows down river valleys at incredible speeds, sometimes over 60 miles per hour. It has the consistency of wet concrete and the power to sweep away everything in its path: bridges, buildings, forests, you name it. The Volcano River Valley, which drains the crater lake, is a natural channel for these destructive flows, and its history is scarred by their repeated passage. The 1953 Tangiwai disaster, where a lahar destroyed a railway bridge leading to a tragic train crash, serves as a stark reminder of their devastating potential. So, how do we live with such a powerful and unpredictable neighbor? Scientists at GNS Science, New Zealand's geological survey, are like volcano detectives. They've wired Ruapehu with a sophisticated network of monitoring instruments, constantly listening for the faintest whispers of an impending eruption. Seismometers are the ears of this operation. They detect ground vibrations from the subtle tremors caused by magma moving deep underground, known as volcanic tremor, to the sharp jolts of small earthquakes as rock cracks under pressure. GPS stations and tilt meters act as the volcano's skin, measuring tiny changes in the ground's shape. As magma accumulates beneath the surface, it can cause the ground to swell or bulge, and these instruments can detect changes of just a few millimeters. Scientists also keep a close eye on the crater lake itself. They regularly sample the water to analyze its chemistry. An increase in certain dissolved gases like sulfur dioxide or carbon dioxide can indicate that fresh magma is rising and releasing its volatile components. The lake's temperature is also a critical clue. A sudden spike in heat can signal that the magmatic system below is becoming more active. All this data flows into a central monitoring station in real time, 24/7, where scientists piece together the clues to assess the volcano's current state of unrest. This brings us to 1995. For months, Ruapehu had been showing subtle signs of agitation. The crater lake temperature was unusually high, and there was an increase in seismic activity. To the casual observer, the mountain looked as peaceful as ever. Skiers were enjoying the slopes, and life went on as normal. It was the calm before the storm. Then, on September 23, 1995, the mountain awoke. A series of powerful phreatomagmatic eruptions began, blasting spectacular columns of ash and steam thousands of meters into the air. The crater lake was completely emptied, its water violently ejected in the eruptions. For weeks, the volcano put on a breathtaking and terrifying display. Ash fell across the North Island, disrupting flights and agriculture. Lahars, thankfully smaller than the historic ones, pulsed on the Volcano River. The 1995 eruption was a classic example of Ruapehu's behavior. It wasn't a single catastrophic bang, but a sustained period of activity. It showcased the complex interplay between the deep magma system, the hydrothermal plumbing, and the crater lake. It also highlighted the incredible importance of the monitoring systems that gave authorities crucial warning, allowing ski fields to be evacuated and areas at risk from lahars to be cleared. Mount Ruapehu is more than just a mountain. It's a living, breathing geological system, a window into the powerful forces that shape our planet. From the deep subduction zone to the explosive surface, every part of its story is a lesson in the dynamic and sometimes destructive beauty of our world. Understanding its past and listening to its present whispers is the key to coexisting with this magnificent giant. Thanks for watching. If you found this journey into the heart of a volcano fascinating, don't forget to like this video and subscribe for more deep dives into the science of our planet. See you next time. But beneath the snow, beneath the ice, beneath the lake itself, changes were occurring that would soon remind everyone why volcanologists never use the word dormant when describing Ruapehu. Throughout the austral winter months of July and August, seismometers scattered across the mountain began recording an increase in volcanic tremor, a continuous low-frequency vibration that suggested magma was moving at depth. The crater lake's temperature began to rise, slowly at first, then more dramatically. By early September, the lake was registering temperatures above 40 degrees Celsius at the surface, far warmer than seasonal norms would predict. The color was changing too. The lake shifted from its winter gray to shades of green, then to a luminous turquoise that spoke of high heat and vigorous gas input from below. Scientists at GNS Science, New Zealand's Geological Research Institute, intensified their monitoring. They recognized these signs as potential precursors to an eruption, but the exact timing remained frustratingly uncertain. Ruapehu had shown similar symptoms before without erupting, and the mountain seemed to delight in confounding predictions. On September 18th, at approximately 4:30 in the afternoon, Ruapehu's patience with subtlety ended. The eruption began not with a gradual buildup, but with explosive suddenness. A column of ash and steam burst from the crater lake, rising several kilometers into the atmosphere within minutes. The sound was heard across much of the central North Island, a deep concussive roar that resonated through the valleys and carried on the wind to towns dozens of kilometers away. Fortunately, the ski season was drawing to a close, and fewer people were on the mountain than there might have been a month earlier. The eruption occurred late enough in the day that most visitors had already descended. But those who remained, including ski patrol members and lodge staff, found themselves facing an immediate crisis. Ash began to fall like dark snow, coating everything in a fine, abrasive powder. The eruption column, illuminated by the setting sun, presented a spectacular and terrifying sight, a towering pillar of debris marking the spot, where the Earth's interior was forcibly making contact with the atmosphere. This initial eruption was just the opening salvo. Over the following weeks, Ruapehu produced a series of eruptions that varied in intensity but maintained a persistent level of activity. Some eruptions were relatively mild, producing ash plumes that rose a few kilometers before dispersing. Others were violent enough to eject blocks of solidified lava the size of automobiles, hurling them hundreds of meters from the crater. Each eruption altered the crater lake, sometimes ejecting so much material that the lake level dropped visibly, other times filling it with fresh volcanic debris that turned the water into a thick, muddy slurry. The most significant phase of the eruption sequence came on September 23rd, when a particularly powerful explosion generated a pyroclastic surge, a ground-hugging avalanche of hot gas and rock fragments that swept down the upper slopes of the mountain. These surges, though relatively small by the standards of some volcanic eruptions, were devastating to anything in their path. They incinerated vegetation, melted snow and ice, and deposited layers of volcanic material that would remain visible for years afterward. What made the 1995-96 eruption particularly noteworthy from a scientific perspective was the opportunity it provided to observe the interaction between the crater lake and the eruptive process in unprecedented detail. Modern monitoring equipment captured data that previous generations of volcanologists could only have dreamed of obtaining. Video cameras positioned at safe distances recorded the eruption columns as they developed, showing the transition from steam-dominated phases to ash-rich explosive events. Seismometers tracked the movement of magma beneath the crater in real time, revealing patterns that would inform eruption forecasting for decades to come. The crater lake itself became a focal point of intense study. Between eruptions, scientists measured dramatic changes in the lake's chemistry, temperature, and level. The lake acted as both a calorimeter, absorbing and measuring the heat input from below, and as a chemical reactor, transforming volcanic gases into dissolved compounds that could be analyzed to determine the composition and degassing rate of the underlying magma. The color changes, which had long been observed but poorly understood, were now being correlated with specific chemical and thermal parameters, creating a more sophisticated interpretive framework. The eruption continued intermittently through the austral spring and into summer, with the last significant explosive event occurring in June 1996. By the time Ruapehu finally settled back into quiescence, the eruption had produced approximately 17 million cubic meters of volcanic material, altered the topography of the summit region, and provided scientists with a wealth of data that would take years to fully analyze and interpret. The eruptions of 1995 and 1996 had reshaped the summit of Mount Ruapehu in ways both visible and hidden. The crater lake, once contained by a natural rim of volcanic rock and ice, had been partially drained during the explosive activity. But in the aftermath, as the mountains settled and winter snow accumulated, a new and more insidious hazard was taking form. On the northwestern side of the crater, the eruptions had weakened a section of the rim, leaving it supported primarily by a temporary dam of compacted snow, ice, and volcanic debris. Behind this precarious barrier, the crater lake slowly began to refill. Scientists monitoring the volcano understood the danger immediately. A crater lake breach was not a matter of if, but when. The question was whether the dam would fail gradually, allowing controlled drainage, or catastrophically, releasing the entire volume of the lake in a matter of minutes. Throughout 1996 and into 1997, monitoring intensified. Cameras were positioned to watch the rim. Instruments measured the lake level as it rose week by week, month by month. Engineers debated intervention should they attempt to artificially drain the lake before nature made the decision for them. The debate became moot on the evening of December 24, 1997, Christmas Eve, a time when most New Zealanders were gathered with family, when the nation's attention was focused on celebration rather than catastrophe. At approximately 10 minutes to 11 that night, the crater rim failed. The trigger was likely a combination of factors: the continued rise in lake level increasing hydrostatic pressure, possible thermal weakening of the ice dam, and perhaps minor seismic activity that provided the final destabilizing push. What happened next unfolded with terrifying speed. Approximately 1.4 million cubic meters of water, roughly the volume of 600 Olympic swimming pools, began pouring through the breach. This was not a gentle overflow, but a catastrophic release. The water accelerating as it carved through the weakened rim and plunged down the steep upper slopes of the mountain. Within minutes, this water had transformed into a lahar, entraining volcanic ash, rock fragments, ice, and snow as it descended. The lahar followed the Wangaihu River Valley, the natural drainage pathway on Ruapehu's eastern flank. The initial flow was moving at speeds approaching 100 kilometers per hour, a wall of debris-laden water and mud that scoured the valley floor and stripped vegetation from the banks. The sound was apocalyptic, a roar composed of countless boulders grinding against each other, trees being snapped like twigs, and the fundamental bass note of thousands of tons of material in violent motion. As the lahar descended from the high alpine zone into lower elevations, it began to slow and spread, but its destructive power remained immense. Everything in the river valley was either destroyed or buried. Hiking tracks vanished beneath meters of volcanic mud. Bridges designed to handle normal river flows were tested against forces they were never engineered to withstand. The lahar reached the Tangiwai railway bridge at approximately 11:49 p.m., nearly an hour after the crater rim had failed. The Tangiwai Railway Bridge was a critical link on the main trunk line connecting Auckland and Wellington, New Zealand's two largest cities. At that precise moment, the Wellington to Auckland overnight express train was approaching the bridge, carrying 151 passengers and crew who had no idea what awaited them in the darkness ahead. The lahar had struck the bridge supports with such force that the structure was already critically damaged, twisted and destabilized by the impact of debris and the scouring effect of the flow. As the locomotive reached the bridge, the weakened structure collapsed. The engine and the first 6 carriages plunged into the raging torrent below. In the dark chaos of Christmas Eve night, 151 souls were hurled into the lahar. The rear carriages, pulled by the weight of those ahead, were dragged to the edge of the broken bridge before the couplings finally snapped, leaving the last car teetering on the precipice. Of the 151 people on the train, only 20 survived. The Tangiwai disaster remains New Zealand's worst railway accident and one of the nation's most profound tragedies. The timing, Christmas Eve, a night of celebration turned to grief, ensured that the event would be seared into the collective memory. But beyond the immediate human cost, Tangiwai represented a devastating lesson about volcanic hazards that extend far beyond the immediate vicinity of a volcano. The crater rim had failed more than 40 kilometers from where the train went into the river. The people on that train had likely never given Mount Ruapehu a second thought as they settled in for their overnight journey. In the aftermath, investigations revealed the cascade of circumstances that had led to catastrophe. The lahar itself had been predicted in general terms. Scientists knew the crater rim would eventually fail. What they could not predict with precision was exactly when the failure would occur or how much warning they could provide. Even if the breach had been detected immediately, communicating that information and halting train traffic in the middle of the night would have been extraordinarily challenging with the technology available in 1997. The disaster prompted a complete reassessment of volcanic risk management in New Zealand. It became clear that monitoring volcanic activity was not sufficient. There needed to be systems in place to detect lahars in real time and to communicate that information instantly to anyone at risk. In the years following Tangiwai, an automated lahar detection and warning system was installed in the Volcano Valley. Sensors capable of detecting the seismic signature and acoustic profile of an approaching lahar were linked to alarms and communication systems that could alert authorities within seconds. For centuries, Mount Ruapehu stood as a silent giant in the heart of New Zealand's North Island, a place of immense cultural significance and breathtaking beauty. To scientists, it was an object of observation, a majestic peak whose behavior was recorded but not deeply understood. But this passive relationship was destined to change. The mountain, with its fiery heart, demanded more. It forced us to move from simply watching to actively questioning, to learn its language before it was too late. The key to this new dialogue was unfound on its icy slopes or in its seismic rumbles alone. It was hidden in plain sight, in the shimmering, mysterious waters of its crater lake. This lake would become our most critical communication channel, a window into the volcano's very soul. The transformation began with a simple observation. The lake's color was never constant. It would shift dramatically from a murky, turbulent gray to a vibrant emerald green, and then settle into a serene turquoise. These weren't just random aesthetic changes. Scientists realized each color told a story, a chemical saga unfolding in the depths. When the water turns gray, it's a sign of disturbance. Vents on the lake floor stir up sediments, clouding the water. This is often accompanied by a rise in temperature, a clear signal that something is heating up from below. As things calm down, the water might turn a brilliant green. This color comes from dissolved sulfur and iron minerals leached from the surrounding rock by acidic, heated water. It's a sign of a complex chemical brew, a direct result of volcanic gases interacting with the lake. Finally, when the system is quiet and stable, the water clears, reflecting the sky in a beautiful turquoise blue, indicating a period of relative peace. Decoding these color changes was like learning the alphabet of the volcano. But watching colors from afar wasn't enough. We needed to be there day and night in all weather. To do that, we needed better tools. The era of manual temperature readings with a bucket and thermometer was over. The solution was a network of autonomous sensors, dropped into the acidic, often steaming waters of the crater lake. These rugged instruments became our tireless sentinels, constantly measuring the lake's temperature, one of the most vital signs of volcanic health. A sudden spike in temperature is often the first and most reliable indicator that fresh, hot magma is rising from deep within the Earth. These sensors don't just collect data. They transmit it in real time via satellite links. This means scientists hundreds of kilometers away can monitor the volcano's pulse second by second. A constant, unbroken stream of information from one of the most inaccessible places on Earth. This technological leap gave us an early warning system we could truly rely on. Beyond heat, the volcano speaks through its breath. As magma ascends, it releases a cocktail of gases. The most important of these are carbon dioxide, sulfur dioxide, and hydrogen chloride. Measuring the amounts of these gases rising from the lake gives us another crucial insight: an increase in the ratio of carbon dioxide to sulfur dioxide, for instance, can suggest that fresh, gas-rich magma is entering the system from deep below. Our scientific toolkit expanded to include specialized gas measurement flights and ground-based sensors. These instruments sniff the air, analyzing the invisible plumes rising from the mountain. By tracking these subtle changes in gas chemistry, geologists can infer what's happening miles beneath the surface, building a more complete picture of the magmatic system's activity and its potential to erupt. It's like being a doctor listening to a patient's breathing to diagnose an illness. This growing understanding led to a moment of unprecedented action in 2007. The 1995 and 1996 eruptions had left a solid dam of tephra, or volcanic ash and rock, blocking the crater lake's natural outlet. As snowmelt and rain filled the crater, the water level rose higher and higher, putting immense pressure on this fragile natural dam. The fear was a catastrophic collapse, which would unleash a lahar, a deadly, fast-moving mudflow of water, rock, and debris down the Wangahu River. This was the same river valley where a tragic lahar in 1953 had caused the Tangiwai disaster. To prevent history from repeating itself, a massive engineering project was undertaken. In a race against time, engineers worked in the harsh alpine environment to build a trench, a controlled spillway through the Tephra Dam. This intervention was designed to safely drain the rising lake water, guiding it away from the path of destruction. It was a bold move, humanity actively shaping the mountain's landscape to protect lives downstream. The project was a success, a testament to what's possible when science, engineering, and a deep respect for the power of nature come together. Today, the vigil on Mount Ruapehu is more comprehensive than ever. The crater lake remains the focal point, but it's just one part of a much larger surveillance network. This modern system, known as GeoNet, is a web of interconnected instruments. Seismometers listen for the faintest tremors that signal moving magma. GPS stations measure millimeter-scale ground deformation, the swelling of the mountain as the magma chamber beneath it inflates. Webcams provide a constant visual feed, while infrasound sensors listen for low-frequency sound waves that can indicate explosions or gas release. All this data flows into a central hub, where it's analyzed around the clock by a dedicated team of experts. It's a symphony of science, where every piece of information, from the color of the water to the subtle stretch of the ground, adds to our understanding. This is the story of how we learn to listen to a volcano. It's a journey from passive observation to active interrogation, from fear to understanding. Mount Ruapehu is still a powerful and unpredictable force of nature, and it will erupt again. But now, we are no longer just waiting for it to happen. We are watching, listening, and learning, engaged in a constant dialogue with the mountain. This ongoing vigil is our commitment to coexisting with this incredible geological wonder, ensuring that we are as prepared as possible for whatever it has to say next. The work never stops, because the mountain never truly sleeps. It is a story of human ingenuity and our enduring quest to understand the powerful planet we call home. Thanks for watching. If you found this journey into the heart of a volcano fascinating, be sure to like this video and subscribe for more stories from the world of science and exploration. Stay curious. The crater lake remains the centerpiece of this monitoring effort, instrumented with sensors that measure temperature at multiple depths, transmitting data every few minutes via a radio link to monitoring centers in Wellington and beyond. Automated cameras capture images of the lake throughout the day, documenting color changes that are then analyzed using spectroscopic techniques to quantify the exact wavelengths being reflected. This allows scientists to move beyond subjective descriptions of greenish or quite blue to precise measurements of the lake's optical properties that can be correlated with chemical composition. Satellite technology has added another dimension to the surveillance. Thermal infrared sensors aboard Earth observation satellites can detect changes in the lake's surface temperature, even when clouds obscure the summit from ground-based cameras. Synthetic aperture radar can measure ground deformation across the entire volcanic edifice, identifying areas of inflation or subsidence that might not be apparent from GPS stations alone. These space-based observations complement the ground-based network, providing a comprehensive view of the volcano's state. But perhaps the most significant advance has been in the integration and interpretation of all this data. Modern volcanology recognizes that no single parameter can reliably predict an eruption. It is the pattern of changes across multiple monitoring streams that provides insight. Scientists have developed sophisticated models that combine seismic data, deformation measurements, gas emissions, and lake characteristics to assess the probability of eruption over various timescales. These models are not crystal balls. They cannot tell you that an eruption will occur at precisely 3:15 next Tuesday afternoon, but they can provide probabilistic forecasts that inform decision-making about aviation alerts, access restrictions, and public warnings. The lahar detection system installed after Tangiwai represents another layer of protection. Sensors positioned in the valleys draining Ruapehu can detect the seismic and acoustic signature of an approaching debris flow within seconds of its passage. When triggered, these sensors automatically activate warning systems that can halt rail traffic, close roads, and alert emergency services. The system has been tested by natural lahars on several occasions and has performed as designed, providing the precious minutes of warning that could mean the difference between evacuation and catastrophe. Despite all these precautions, living in the shadow of an active volcano requires accepting a certain irreducible level of risk. The ski fields continue to operate on Ruapehu's slopes during winter months, with detailed emergency plans and eruption response protocols in place. The tourism industry that depends on the mountains generates significant economic activity for the region, creating a constant tension between safety imperatives and economic interests. Authorities must balance the cost of false alarms, which can devastate the tourism sector, against the unacceptable cost of failing to warn when a genuine threat materializes. The Maori communities who have lived with this mountain for centuries maintain their own relationship with Ruapehu, one that acknowledges both its beauty and its power. The concept of tapu, of sacred prohibition, serves as a cultural framework for respecting the mountain's dangerous nature. Traditional knowledge about the mountain's behavior, passed down through generations, complements scientific monitoring, providing a longer historical context than written records alone can offer. As climate change alters precipitation patterns and glacial dynamics, new variables enter the equation. The amount of ice and snow on Ruapehu's summit fluctuates with changing temperatures, potentially affecting the volume of water available to generate lahars. Scientists are working to understand how these environmental changes might modify the volcano's hazard profile, adding yet another layer of complexity to an already intricate system. There's a particular quality to standing at the edge of Ruapehu, this crater lake, on a clear day, when the turquoise water reflects the sky and steam rises gently from the surface like breath in cold air. It is beautiful in a way that transcends simple aesthetics, beautiful in the manner of all things that contain both creation and destruction in the same moment. The lake sits there, serene and terrible, a body of water that has witnessed more violence than most battlefields, yet appears as tranquil as a mountain tarn on a postcard. This lake remembers everything. In its chemical composition lies the signature of every eruption, every influx of magma, every period of dormancy. The sediments at its bottom contain layers of ash and rock fragments that tell the story of the mountain's fury in a chronological archive more precise than human memory. Scientists who core these sediments are reading a history book written in volcanic glass and altered minerals, deciphering events that occurred long before anyone was watching, before monitoring networks existed, before the first Maori voyagers sighted these islands from their ocean-going canoes. What the crater lake teaches, above all, is humility. For all the instruments, all the models, all the accumulated knowledge of modern volcanology, we are still observers trying to predict the behavior of a system far older and more complex than our understanding. The lake changes color, and we can measure the wavelengths and analyze the chemistry. But the exact moment when observation becomes warning, when data becomes decision, when probability becomes certainty, these thresholds remain frustratingly imprecise. The people who live and work around Mount Ruapehu have learned to exist in this state of informed uncertainty. They check the monitoring websites, note when the lake turns from green to blue, pay attention when seismic activity increases. But they also ski the slopes in winter, hike the trails in summer, and go about their lives with the pragmatic acceptance that absolute safety is an illusion anywhere on this geologically active planet. New Zealand sits astride the boundary between two tectonic plates, and this fundamental reality shapes not just the landscape but the national character, a certain resilience, a willingness to rebuild, a dark humor about living on shaky ground. The future of Ruapehu's crater lake is written in the same forces that created it: the relentless subduction of oceanic crust, the generation of magma in the mantle below, the episodic rise of that magma toward the surface. These processes operate on timescales that dwarf human lifespans, yet they intersect with human time in moments of eruption and catastrophe. The lake will continue to change color, will continue to heat and cool, will continue to serve as the visible manifestation of invisible processes occurring kilometers below. Perhaps in another 50 years, monitoring technology will have advanced to the point where eruptions can be predicted with near certainty, where the precise moment of crater rim failure can be calculated days in advance. Perhaps artificial intelligence will find patterns in the data that human analysts cannot perceive, translating the lake's chromatic vocabulary into predictions of startling accuracy. Or perhaps Ruapehu will continue to guard some essential unpredictability, some irreducible element of surprise that reminds us that nature does not operate for our convenience, or according to our schedules. What seems certain is that the lake will remain, changing its colors through the seasons and the centuries, a pool of water heated by the planet's interior and exposed to the sky above, existing at the intersection of two realms. It is both thermometer and cauldron, both warning system and weapon, both object of scientific study and source of sublime beauty. The M'a-ori concept of tapu seems particularly appropriate for such a place sacred, not in the sense of gentle holiness, but in the sense of power that demands respect of forces that humans can observe and measure, but never truly control. Standing at that crater rim looking down at water that might be a pleasant swimming temperature or hot enough to scald, colored green or blue or gray by chemicals that speak of the Earth's restless interior, one feels the appropriate emotion. Not fear exactly, but something closer to awe. Awe at the intricate mechanisms by which our planet regulates its internal heat. Awe at the delicate balance between catastrophe and quiescence. Awe at our own audacity in trying to predict when that balance will shift. The lake will change color again. The mountain will erupt again. And humans will continue to watch, to measure, to interpret, and to hope that when the next crisis comes, the warnings will be heard and heeded in time. Mount Ruapehu's story is far from over. The crater lake continues its chromatic conversation with those patient enough to listen, and somewhere beneath the snow and ice, magma moves through ancient pathways following rhythms that predate human civilization and will continue long after our cities have crumbled to dust. If this journey into the heart of a restless volcano has left you with that same sense of awe, if you find yourself wondering about the other mountains that breathe fire, the other lakes that boil, the other places where Earth's interior breaks through to remind us of the forces churning below, then we invite you to continue this exploration with us. Subscribe to Fury of the Earth, where every story is a window into the planet's most powerful forces. We bring you the science, the history, and the human drama of geological events that have shaped our world, told with the depth and elegance they deserve. If this story resonated with you, share it with someone who appreciates the extraordinary reality that we live on a dynamic, ever-changing planet. Sometimes the most important conversations begin with a simple question. Did you know there was a lake in New Zealand that changes color to warn us when a volcano is waking up? The Earth is always speaking. The question is whether we're listening carefully enough to understand what it's trying to tell us. Until the next eruption, until the next story, keep watching the mountains. Some of them are more awake than they appear,